Okay, so till now we have been dealing with this differential amplifier, and you must have noticed that I have used this constant current source at the source, and we had done that earlier also when we were dealing with differential amplifier with resistive loads, and then we replaced the current source with a more realistic thing, and that was a current mirror based configuration. And what did that do? What effect did this transistor have? The effect this transistor had was on the common mode response of the circuit, right? Because why am I saying common mode? Why not differential? Because if you consider differential modes, right? So then if this is plus delta V, this is minus delta V, then the total voltage swing at this node Vx is 0, right? If the total voltage swing is 0, then essentially the existence of this external resistance, existence of this RDS, right? This parasitic resistance of M0 is irrelevant because no current is flowing through R0, right? However, if we have common mode excitation, let's say we have plus delta V here and plus delta V here, right? Then what? Then we cannot neglect, right? Because if this happens, then what is the voltage swing here? This is approximately equal to delta V, right? So as far as the voltage swing at this node Vx is concerned, that is same. That was almost equal to delta V in the previous architecture. So do you think it's the same in this architecture? It's kind of the same, right? Why am I saying it's kind of the same? It's because nothing has changed. If I look this side, something has changed on the top side, but nothing has changed on the bottom side of the as far as the working of M1 as M2 is concerned, right? So it's quite natural for us to expect that the voltage swing at this node Vx is almost equal to delta V, correct? So okay, fine. If that is the case, now note that it cannot be exactly delta V. If it's exactly delta V, which means that there cannot be any incremental current through M1 and M2. So this is approximately delta V, right? So if that is approximately delta V, what is the current through R0? So since we are doing common mode excitation now, so I can as well get rid of let's do incremental, right? So if I are doing incremental, then we can get rid of this M0 and all these things, right? So what is the current through R0? Current through R0 becomes delta V, or let me call it VCM, right? Instead of delta V, let me call it VCM, small VCM. So that helps us and make the point that we are talking about incremental common mode excitation, right? So if this is also approximately VCM, so what is the current through R0? Current through R0 is VCM by R0. So where will this R0 flow once it reaches that node Vx? It will get split into two branches equally, right? So it will get split into two branches equally. So this will be VCM over 2 R0, and this will be also VCM over 2 R0. Now note that why are we doing this? We are trying to find out the common mode gain of this architecture, right? We already found out the differential equivalent of this architecture. Differentially, that equivalent transconductance was the GM of M1. We now are trying to figure out what is the common mode response of this architecture, right? So in order to do that, let's incrementally short this also, because otherwise we would like to normalize everything in the end, right? Okay, so if this is VCM by R0, this VCM by R0 on the left branch that is flowing through M1 flows through M3. This is also VCM by 2 R naught. Correct? So this current gets copied through M4. So this becomes VCM by 2 R naught. So what is the current that is flowing into the incremental short? This is 0, right? VCM by 2 R naught is coming from top, VCM by 2 R naught is being dragged out. So essentially the incremental current into the short is 0, right? What does this tell you? This is essentially telling us that the common mode response of this network is, this network doesn't respond to any common mode excitation, right? That's what it's telling us. But whenever you get something to be 0 or infinity, then you have to step back and start thinking, did I neglect something because of which we are getting 0? Because note that we cannot neglect anything with respect to 0, right? Okay, so what are the things you think we might have neglected? So we neglected channel length modulation. We neglect channel length modulation for M3 and M4, right? So if we don't neglect that, right? If we don't neglect that, what's going to happen? So let's put in channel length modulation, which means that we have R3 and we have R4. But R4 is irrelevant because both sides of R4 are shorted, right? So I can essentially say that channel length modulation of M4 is irrelevant. So that goes out of the window. Okay. So what about this VCM by 2 R naught? Where does this VCM by 2 R naught go? VCM by 2 R naught goes and develops a voltage at this node. What is the impedance looking up? What is the impedance looking up? The impedance looking up is 1 over GM3 plus GDS3, right? If that is the impedance looking up, what is this voltage? This voltage becomes minus VCM by 2 R naught times 1 by GM3 plus GDS3. Correct? So at this time you might be telling me, hey, why don't you neglect GM3 now? Why don't you neglect GDS3 now? So the reason I am not neglecting GM3 is the following. So if we neglect GDS3 with respect to GM3, what will be the current through M4? The current through M4 will be GM3 times this, correct? GM3 times this in the direction pointing down, right? GM3 times this with including the negative sign in the direction pointing up. But if I flip the current direction, this will become GM3 times VCM by 2 R naught times 1 over GM3, which means again we'll be getting VCM by 2 R naught pointing down. So neglecting GDS3 will lead to the same answer, that is 0, right? So we are trying to figure out if neglecting channel length modulation has caused a problem or not, right? So we cannot neglect it now. So if this is the case, what is the current through M4 in the direction pointing downwards? This will be GM4 by GM3 plus GDS3 times VCM by 2 R naught. Using the incremental model, you can as well say it's pointing upwards with a minus direction, right? Because VG is negative, right? But I can as well say I flip the current direction and point it towards the ground, towards bottom, right? Okay, fine. If this is the case, so this is almost equal to what? This is not almost, exactly equal to if GM3 and GDS3 are same, GM3 and GM4 are same. So this becomes, let's say, GM4 by GM4 plus GDS3 times VCM by 2 R naught, right? Do you think there is less than VCM by 2 R naught or greater than VCM by 2 R naught? This is clearly less than VCM by 2 R naught, right? So essentially there will be a difference current that will flow. There will be a difference current that will flow in this through this short, right? In order to, if I write KCL at this node, I should see an extra current flowing through the short. What will be that extra current? So ISC, what will be ISC? ISC will be VCM by 2 R naught minus this new guy, right? So essentially VCM by 2R0 1 minus GM4 by GM4 plus GDS3. Right, GDS3 and GDS4 are same, so let me put GDS4. So this becomes VCM by 2R0 times GM, right, times GDS4 by GM4 plus GDS4. Now I can neglect GDS4 with respect to GM4, right? Because I mean we have solved that problem of things getting cancelled and becoming 0, right? Okay, so this becomes a short circuit current, right? Note that if we neglect GDS4, right, if GDS4 becomes 0, then clearly our short circuit current also becomes 0, right? So okay, so this becomes a short circuit current. And what is the common mode what is the incremental equivalent for a common mode differential, for the common mode input in a differential amplifier? So for common mode inputs, the incremental equivalent becomes note that in this case the current direction is this, right? Because the current is flowing from the short into the device, so the current direction reverses, and this becomes VCM by 2R0, right, times GDS4 over GM4 times GDS4 over GM4. And what is output resistance? Output resistance doesn't change. That is whatever we figured out in the previous module, that is RDS2 parallel RDS4, right? So this becomes the VOCM. So this becomes VOCM. And right, and for differential mode, what was it? What was the equivalent what was the equivalent Norton, what was the Norton equivalent? The Norton equivalent was GM times VDiff, right, GM times VDiff, and output resistance remains RDS2 parallel RDS4, right? So this would have been the differential mode equivalent, right, VODiff of our differential pair, correct? So this part we have dealt it in detail. This is the new part. And what is the observation? The observation here is, there are twofold observation. You ideally would want the common mode response to be 0, right? So under what condition do you see the common mode response becoming 0? There are two cases. If we neglect the channel length modulation of the tail transistor, which means R0 tends to infinity, then the incremental current, the incremental common mode current goes to 0. That makes sense because that is equivalent to saying we are using a ideal current source at the tail node. Alternatively, if we neglect the GDS, if we neglect the channel length modulation of M3, then also we see that we are likely to get 0 common mode response, right? So what does it translate to in terms of designer's choice? In terms of designer's choice, if you are looking to get low common mode rejection, right, or rather high common mode rejection or low common mode response, then you have to do one of these two things. Either you cannot ever have an ideal current source, but you have to make R0 to be larger. How do you make R0 larger? R0 for the tail transistor larger? You have to increase the length of the transistor, right? You have to increase the length of the transistor, and if you don't want to impact the current, then you have to increase the W also. Essentially, you have to increase the size of the device. So that will help in increasing the R0, right? Similar things you'll have to do in case of M3 and M4 as well, right? So that will give you decent common mode rejection. Okay. So before we stop on this differential pair, let me talk about one more specification that is also quite vital while trying to figure out while trying to design a differential pair, and that is the range of inputs, the range of acceptable inputs that your our transistor can take, right? So let's say I have, this is biased, let's say M0 is biased with a constant current source, and you have some VGSQ, right? So we know how to do this, we are not particularly bothered. And let's say I0 is here, and here I have VCM and I have VCM. Okay, fine. So what essentially I am asking is, what is the limit of when we apply an input, right? When we apply input, we are applying the input to the inputs of M1 and M2, right? So if we have transistors biased using VCM, essentially what we are asking is, how far can you push the VCM up or down before the transistor goes out of its operating region, right? Or rather, which transistor will start going out of its operating region? That is of interest to us. Okay, so for that we need to first understand what are the bias points, right? If we know the bias points, if we know the quiescent voltages and currents of all nodes, then it's easy to figure that one out, right? So let's do that. So let's assume that, even before we assume, let's see which bias points we know accurately. If things are biased properly, right? If things are biased properly, this current through M1 is I0 by 2, current through M0 is I0 by 2, right? What is this voltage? This voltage will be VDD minus VSG of M3 for a bias current of I0 by 2. This we also know. What is the voltage at V0? This we don't know, right? Because that is a high impedance node, right? That is the node that is giving us gain. So we don't know exactly what is that voltage, because the current through M2 and M4 can as well be I0 by 2 for a range of voltages of V0, right? Because that's the drain voltage of M2 and M4, and ideally a change in drain voltage should not lead to any change in current, right? So which means that multiple solutions for V0 is possible, ideally. Okay, so which means that we have to assume certain value of V0. So let's assume V0 is at some V0 CM or some V0 Q, and that V0 Q has to be set by some external factors. We haven't yet seen how the external factors set V0 Q, but let's assume it's set, right? It's given to you by somebody. So the now question that we are asking is, what is VCM max and what is VCM mean? This is equivalent to the swing limits condition that we have done for single transistor circuits, right? Okay, so what do you think? How should we go about doing analyzing this? So let's do the VCM min first, because you will see that this is slightly simpler to, there is a continuity to what we are doing. So what do you think is likely to happen if I connect these two nodes and yank them up and down, right? They are connected at VCM. I connect VCM up, I pull VCM down below its quiescent point. What's going to happen? So this is equivalent to saying that I have a common mode excitation, right? I am pulling VCM down, and this is equivalent to saying that I have a common mode excitation. So if VCM goes down on both arms, which node is, do you think the current will change? If I assume that if I neglect channel length modulation and all, right? If I neglect channel length modulation of M0, do you think reducing VCM will change current? No, it won't, right? So, but what is going to change? Because the current is not going to change, the VGS of M1 and M2 will remain constant, right? If VGS remains constant, the node voltage of Vx is supposed to drop, right? Because I am dropping the gate voltage, so Vx is supposed to drop. So what is Vxq? Vxq was VCM minus VGS of M1 for a current of I0 by 2, which is same as VCM minus VGS of M2 for a current of I0 by 2, right? So what is the minimum that Vx can go? The minimum Vxq min is essentially the overdrive voltage of M naught, right? It's VGSQ minus the threshold voltage, right? So this is V overdrive of M naught, right? Which means what? Which means therefore VCM min is Vxq min plus VGS of M1 for a current of I naught by 2, which means the minimum VCM becomes V overdrive of M naught plus VGS of M1 for a current of I naught by 2, right? So this is VCM min. Right? Do you think anything else is going to affect? Do you think the voltages at the gate of M3 is going to change? No, right? Because the current hasn't changed, the voltage at the gate of M3 is not likely to change, correct? Okay. So often this VCM min is also called input common mode range, the lower limit, right? So this is ICMR minus, right? So this is often called ICMR minus. This is abbreviation of input common mode range lower limit. The minus corresponds to the lower limit. Okay. So let's see what's going to happen to the upper limit then. Okay. So let's see that. So now let's assume that we are yanking this voltage up. We are yanking this voltage up. Okay, we are yanking VCM up both sides. So what do you think is going to happen to Vx? This Vx is going to increase, right? Because VGS has to be same. So do you see a problem with M0 going out of saturation? No, obviously not, right? But what is likely to be the problem? So if VCM increases, if current doesn't change, if I neglect channel length modulation, do you think the gate voltage of M3 or do you think the drain voltage of M3 is going to change? No, because current hasn't increased. So current hasn't changed, which means what? How far can I raise VCM? I can raise VCM till we reach, right? So VCM, or rather the condition is the drain voltage of M1 has to be, the drain voltage of M1 has to be greater than equal to the gate voltage, this is VCM minus 1 threshold voltage, right? Which means that VDD minus VSG of M3 has to be greater than VCM minus 1 threshold voltage, right? So which means that VCM has to be less than VDD plus 1 threshold voltage minus VSG of M3, right? So this is as far as the constraint on, this is constraint on M1, right? M1 in sat. What about M2? So M2 in sat, what will be the constraint? So note that instead of the drain voltage of M2 is what? Is VOQ, and as we initially assumed, VOQ is being set by something else. We don't know what it is. So essentially, whatever is setting VOQ will end up having an impact on how far the gate voltage of M2 can go, and in that case, what will be the constraint? It will be VCM should be less than equal to VOQ plus threshold voltage M, right? So what will be the maximum VCM? The maximum VCM will be the minimum of this and that, right? So minimum of, so ICMR plus will be minimum of VOQ plus VTHN or VDD plus VTHN minus VSG of M3, right? Whichever is smaller will be your input common input range, upper limit range. Beyond this, you will not be able to use increase VCM. So this is an important parameter, because ultimately when you are using a differential amplifier, you need to know till what range you can give your inputs. You cannot apply any input or of any range, right? So that becomes an important parameter, right? So before we stop on this single stage differential amplifier, what I would like to point out is everything that we have developed till now has been by using an NMOS transistor, right? So in other words, so this is what our circuit has been right from the beginning, right? So this is what the circuit has been right from the beginning, at least right from the beginning of today's lecture. But whatever we have been doing till now has been under the condition that the input is being applied to an NMOS transistor. Just like in case of a common source amplifier, we started off with an NMOS transistor. In case of a differential amplifier also, we started off with an NMOS transistor. We assume the input is being applied to the NMOS transistor. But equivalently, you can have a complementary scenario where the input is applied to a PMOS transistor. So essentially we flip the entire thing. Just like in case of a common source amplifier with an NMOS input, we could have flipped it and made it a PMOS input. So we can do the same thing here. And if we do that, what's going to happen? I mean, we use the same principle. Current flows from higher potential to lower potential. In case of a PMOS transistor, the current will flow from a source to drain, right? So let's replace one transistor at a time. Whatever is NMOS will make it PMOS, whatever is PMOS will make it NMOS, and let's see what happens, right? So let's see. So in case of M1, so let's say the equivalent for, so this is the PMOS equivalent, PMOS input differential pair, Diff-amp, right? So M1 is NMOS in our case. So M1, let's replace M1 with a PMOS transistor. So let's replace M2 with a PMOS transistor. So let's call this M1 here, M2 there. Okay. So where will, what will be the current direction in M1 and M2? Naturally, the quiescent current flows from source to drain. So the quiescent current here has to flow from, it has to be I0 by 2 from top. Correct? So in case of the NMOS equivalent, what is connected to the source? We have a current source connected to the source. Essentially, this is this thing, right? This is an I0 connected to the source, right? I am sinking current out of the source. In case of a PMOS, I should be sourcing current of I0. Correct? Okay, fine. So what is, now let's replace M3 and M4 in the differential, in the circuit in the left. M3 and M4 are PMOSes. We'll make them NMOSes, right? So let's make them NMOSes, and their gates are connected, the sources are connected. And what is connected to the source? In case of the circuit on the left, the source of PMOS is connected to the highest potential VDD. In our case, the M3 and M4 source will be connected to the lowest potential, that is ground. What should we do with the drain and the gate of M3? In the circuit in the left, the drain and the gate of M3 are shorted. Here also we do the same thing, and we apply VCM here, VCM here, and if we have to apply an input, we can apply an input just like this, right? So now if we have to replace this I0, what can I do? We go back to the transistor level equivalent. This is M0. So if you have to replace that I0, we replace this with a current mirror, a PMOS current mirror, which we have done multiple times before, right? So this is a known circuit. right? So this becomes a PMOS equivalent differential amplifier, right? So whatever is valid for the circuit on the left is also valid for the circuit on the right. Incremental equivalent is identical, right? So incremental Norton equivalent is identical for both the circuits, because incrementally there is absolutely no difference between an NMOS and a PMOS transistor. But what will be different? What will be different? The difference will be in terms of quiescent points, right? So what I would request you to do is solve for whatever we have done, right? ICMR plus, ICMR minus, output resistance, right? GM, flow of current, directions, right? All these things for the PMOS equivalent yourself, right? Okay, thank you.